Now that we've seen how galvanic cells are designed, built, and cause electrons to flow due to a spontaneous redox reaction, let's look at cell notation, which is a convention for representing galvanic cells in textual form. We're also going to look at the thermodynamics of cells and connect, for example, the voltage across a cell, which we'll write as Ecell, to the delta G associated with the spontaneous redox reaction that occurs within the cell. So galvanic cells can differ in their chemical components, the chemical components of the cathode and anode, as well as the concentrations of those components in the aqueous phase. The textual convention for galvanic cells, called cell notation, encodes these differences in a textual form. And the general convention to remember, the mnemonic to remember when thinking about cell notation, is ABC. We write the anode first, followed by two double lines to represent the salt bridge, and then the cathode. To write the anode and cathode half cells, we list the reactants and products for the oxidation and reduction reactions respectively. We separate those components with a single vertical line. We list reactants first and then products according to the spontaneous redox reaction in the spontaneous direction of reaction. So we'll need the spontaneous redox reaction in order to write cell notation for a galvanic cell. If we're under non-standard concentrations or pressures, non-standard conditions, we need to list these in parentheses after the components with which they're associated. If we don't list them, then it's assumed that we're under standard conditions, which are 1 mole per liter of all aqueous components and 1 bar of pressure for all gases. And we want to include phase designators so that we know the phases of the various components of the galvanic cell. Let's practice writing cell notation for the example of our aluminum-copper cell that we've seen before. So this copper-aluminum cell involved the spontaneous oxidation of aluminum metal by copper 2+ ions, which are in solution and have that nice blue color. Spontaneously, aluminum is oxidized. 2 of these are oxidized to form 2 aluminum 3+ cations. 3 copper 2+ ions are then reduced to form 3 atoms of copper metal solid, which played out onto the piece of copper metal. So this is the direction of spontaneous chemical change. The reaction goes spontaneously in this direction within the cell. To begin writing cell notation, we need to notice that aluminum is being oxidized within the anode. The left-hand half cell in our drawing here is the anode, while copper 2+ is being reduced within the cathode. So just like we've seen before, oxidation occurs within the anode, while reduction occurs within the cathode. Since according to the convention we write the anode first, let's start with the aluminum and aluminum 3+ half cell. The way the reaction is written in the spontaneous direction, aluminum metal is a reactant, and the aluminum 3+ aqueous, with which that aluminum metal is in direct contact, is a product. So we use a single vertical line to separate these components that are in direct contact. A salt bridge connects this half cell to the cathode. Within the cathode, copper 2+ ions are serving as a reactant, and this solution of copper 2+ ions in water is in direct physical contact with a piece of copper metal, and copper solid is the ultimate product. In red on the right-hand side of the cell notation we have the cathode. And notice that the cell notation has both the oxidation reaction occurring within the anode and the reduction reaction occurring within the cathode encoded into it. And the spontaneous directions for these reactions are from left to right within the cell notation. Furthermore, we can see the spontaneous direction of electron flow by noticing that electrons flow from the anode to the cathode, from the aluminum metal through the wire and to the copper 2+ to form copper solid. This is the beauty of cell notation. In reading it from left to right, we get the spontaneous oxidation reaction, the spontaneous reduction reaction, and the direction of electron flow from left to right. Let's now clarify this idea of the voltage across a cell and talk in a little more detail about what cell voltage represents. Cell voltage is really just an electrical version of energy that's more convenient to measure than, say, joules per mole. Keep in mind the definition of the volt. Energy in joules is equal to voltage times charge, or V times Q. That means that 1 volt is equal to 1 joule per coulomb. And to bring this into a little more focus, I want to actually draw an analogy to gravitational energy. You may recall that gravitational potential energy can be represented as the mass of an object times the acceleration due to gravity times the height of that object off of the ground. So if we had, say, a mass m that was a certain height h off of the ground, its gravitational potential energy would be its mass times g times the height. If we wanted to calculate the force due to gravity on this object, well, that's the energy divided by the height, right? And it's going to be the mass times the acceleration due to gravity, mg. We can do something similar with electricity, noticing that electrical energy is equal to the voltage times the charge. If we divide both sides by the charge, we get what we can think of as electromotive force, or EMF. That's equal to the energy divided by the charge in the same way that the gravitational force is equal to the gravitational energy divided by the height. So charge here is playing the role of height here in the gravitational analogy, and that's why we call voltage electromotive force. It's the force on a charge Q due to some electrical potential energy field. Ultimately, you'll want to keep in mind that a volt is 1 joule per coulomb. Now, confusingly, instead of using V for voltage, we'll use E or Ecell for cell voltage, and the E is just meant to evoke electromotive force. This is what voltage is. It's the electrical force on a charge Q. Instead of using E to represent energy, we'll actually use delta G, Gibbs free energy, since our idea is to relate this, which is a chemical energy, back to Ecell, which, when taking into account the charge transferred, really amounts to an electrical energy. The free energy released by a spontaneous redox reaction is converted into positive electrical work. That means that when we relate delta G to the cell voltage, it will be negative cell voltage times some proportionality constant that's equal to delta G. We use the negative sign since the energy released by a redox reaction, which will be negative since the reaction is spontaneous, is translated into positive electrical work, and Ecell by convention is always positive. What's the proportionality here? Well, check out the definition of the volt above. 1 joule is equal to 1 volt, which we've got in the form of Ecell, times 1 coulomb. How do we represent this? Well, this is just some charge Q, and for a redox cell, for a galvanic cell relying on a redox reaction, this Q is the number of electrons transferred times the charge per electron. Number of electrons cancels out, and we're just left with the total charge transferred over the cell in execution of this redox reaction. So backing up, we can write this out explicitly, first by calling this constant, that's the charge per electron, F. And in fact, it's not the charge per electron, it's the charge per mole of electrons. Since we're chemists, we use moles as a counting unit, and this number of electrons transferred is just the number in moles. This constant of charge per mole of electrons is known as F, Faraday's constant. If we represent the number of electrons transferred as N, we get that delta G is equal to negative Ecell times N times Faraday's constant. Delta G is equal to negative Ecell times N times Faraday's constant, and actually you'll see this written most commonly as delta G is equal to negative N F Ecell. This is true for any electrochemical cell under standard conditions or not. The free energy change of the redox reaction is equal to negative the number of electrons transferred times Faraday's constant, that's coulombs per mole of electrons, times Ecell in volts. What this means is that the cell voltage Ecell is really just an easily measurable proxy for delta G. It's simple enough to convert Ecell into a delta G value just by examining the redox equation and finding N, and then looking up F, or just knowing the value of F and plugging it in right there. So there's an electrochemical triangle here. We've just related delta G to Ecell, and let's write that relation in terms of Ecell. So dividing both sides by negative NF, we get that Ecell under standard conditions is equal to negative the standard molar free energy change for the redox reaction divided by NF, the number of electrons transferred per mole of reaction events, times F, Faraday's constant, in coulombs per mole. This allows us to go from an Ecell to a delta G and vice versa. We also know how the standard molar free energy change is related to Kc, namely delta G under standard conditions per mole of the redox reaction is equal to negative RT natural log of Kc. So we can of course relate delta G to Kc. But now we can combine these two relations together and substitute in this negative RT natural log of Kc for the delta G of reaction in the numerator of this Ecell expression to relate Ecell to the equilibrium constant Kc. And so doing that, we get that the standard cell voltage is equal to positive now RT divided by NF natural log of Kc. This is a form of the standard cell voltage that we're going to see later in discussions of the Nernst equation. So this electrochemical triangle, so to speak, is pretty powerful, but it's important to keep a few things in mind. First of all, standard conditions are defined as 1 mole per liter of all aqueous components and 1 bar of pressure for all gases. These particular relations apply only under those standard conditions. That's what the little circle means, although it's not too difficult to generalize these if we think about Q instead of Kc. One way to gain entry to this cycle of electrochemical and thermochemical values is to use free energies of formation to calculate the standard delta G. We can then use that delta G to calculate Ecell from there, for example, but that's kind of a pain, especially when we're working in an electrochemical context where we can just measure Ecell directly. Note that measuring Ecells actually provides us another way to find standard free energies of reaction. We just construct a cell under standard conditions and measure the resulting voltage. Question arises though, can we develop a standard library of cell voltages that we can add and subtract in the same way we would add and subtract free energies of formation to calculate standard free energy changes? This would be really nice because rather than measuring Ecell for every new cell we construct, we could use these standard cell voltages to make theoretical predictions for cell voltages without ever actually building and measuring the cells. In fact, we can do this by defining a specific standard electrode and a standard process for everything that we hook up to this electrode. We then get standard cell voltages actually for half cells relative to this standard electrode, and we can add and subtract those in a Hess's law-like way to find standard cell voltage. We'll see what that looks like in the next video.